Warm welcome to everyone today at our 18th INFOGEST Viva webinar. Today, I'm your host, Shannon Gwala, and I'm joined by Daniela Freitas, and we're going to be facilitating the webinar for you. And our speaker today is Marluci Ghiraldi from Brazil. Marluci graduated with a PhD in food engineering sciences from the University of São Paulo in Brazil, and she was under the supervision of Samantha Pinho. She will present her talk today entitled The Impact of Microstructure on Hybrid Gels on the Bioaccessibility of the Vitamins B12 and D3 through in vitro digestion for elderly in about 21 minutes. So this will be followed by a question and answer session, which will be live. Do use the Q&A button below to drop in questions as she's going through her talk. So for now, we will move to the pre-recorded video and listen to that. Thank you very much.
Hi everyone, I'm Marluci Ghiraldi, and today I present part of the work done during my PhD. Looking to the impact of the microstructure of hybrid gels on the bioaccessibility of vitamins B12 and D3 through in vitro digestion for elderly. Supervised by Samantha Pinho in the University of São Paulo. In the introduction, I'll establish the connection among these four aspects: the target, the bioactive, the source, and the structure. The target of our project was the elderly people. The percentage of people aged 65 years old or older worldwide is estimated to rise from 9 to 16% in 2050, and this demographic transition is a change, mainly related to life quality as older adults undergo significant changes in their physiological process, like the body composition and gastrointestinal changes. The gastrointestinal tract changes are associated with malabsorption of vitamin B12 due to reduced gastric acid production, and the body composition changes are associated with the decline of 7-hydrocholesterol reserves in the epidermis during aging, impacting vitamin D absorption, and also the progressive loss of skeletal muscle mass quality associated to malnutrition, especially the tendency of elderly people to consume less than the recommended dietary allowance of protein. For these reasons, the bioactives that were added to our matrix were vitamins B12 and D3. Also, from a technological point of view, we chose to work with a hydrophilic and a hydrophobic bioactive. Vitamin B12 refers to cobalamin compounds, and according to the radical link to cobalt, it receives a name. For example, when this radical is cyano, it's called cyanocobalamin. And on the other hand, vitamin D3 or cholecalciferol is a hydrophobic compound. It has a hydroxyl group in its carbon chain. Therefore, it has good solubility in alcohols such as methanol and ethanol. And dementia and muscle weakness happen when people are with deficiency of these vitamins. So we decided to incorporate these vitamins into a hybrid protein matrix, since proteins are amphiphilic compounds capable to interact with both hydrophilic and hydrophobic compounds. And why mixing animal and plant proteins? These foods are increasingly being introduced into the market to meeting global protein demands because the higher availability and diversity of plant proteins, because of a new group of consumers that are the flexitarians that's growing, people who cares about health and sustainability without giving up the sensory experience and nutrition associated with animal proteins. They replace part of the animal proteins that they consume. by plant proteins. So we choose to work with commercial proteins, and to compose the hybrid gel we choose the soy protein isolate as plant ingredient, the SPI, and the whey protein isolate, WPI, as animal ingredients. SPI is one of the most common plant-based ingredients in foods on the market nowadays. And Brazil is the world's largest soybean producer. And WPI is a common source of protein supplementation with a consolidated market and well accepted by consumers. So mixed protein gels was chosen as the matrix because it can be formulated according to the needs of elderly consumers with high protein content and capable to carry vitamins in structures. And we choose 3 mixing ratios. That's 70% of SPI, half and half, and 30% of SPI with 70% of WPI. And how to simulate this physiology of elderly. To design an delivery system for these proteins and vitamins, we use in vitro method based on a consensus protocol, the INFOGEST, but we consider the changes in the physical, chemical, and physiological conditions of the gastrointestinal tract of the elderly. We carried out these experiments in 2022, and at that time, consensual protocol for the elderly had not yet been published. So after review and based on some previously published papers, we choose our parameters that I will show in the measuring methods. So the aim of our work was to establish the relationship between the structure of protein-rich hybrid gels on proteolysis and bioaccessibility of vitamin B12 and D3 through analysis of elderly in vitro digestion. To do that, first we need to develop the mixed protein gels and analyze the microstructure and the rheological properties of these gels. And after that, we did the elderly static in vitro digestion to access the protein hydrolysis and vitamins bioaccessibility, and correlated this protein hydrolysis and vitamin bioaccessibility with the microstructure of the gel. We had this part of the work published this year in Food Structure, and this part corresponds to the chapter 3 of my thesis that was compiled by 5 chapters, I think. And but first I will explain a part of my chapter 2 that's not in this article, because one of the challenges of work with plant proteins is their low solubility. So the beta-conglycinin and glycinin are the major proteins of SPI, and they are easily denatured during the industrial production of commercial SPI, result in aggregates that decrease the solubility. So to increase the solubility, we homogenize this dispersion using a combination of 2 methods: mechanical stirring using this overhead stirrer plus ultrasonication. So initially, the soy proteins formed heterogeneous aggregates, and after this homogenization treatment, the dispersion was more fluid. And after the process of heat-induced aggregation and proteins gelation, we can see the formation of large aggregates in the gel without treatment. And after the homogenization, combined mechanical stirring and ultrasonication, the aggregates decrease in size. So, after we established these parameters, we produced the mixed protein gels we first produce two different dispersions, one for SPI using that parameters and one for WPI. And after that, we mixed them, and then we added vitamin D, solubilized in ethanol, and vitamin B12 solubilized in water, and a salt. Again, we mix them, hydration overnight, and we produce the heat set gels, heating at 95 degrees for 30 minutes. The gels present a pink color due to presence of vitamin B12, WPI only gel, and SPI only gel was the control gels. The protein structure of WPI only gel was formed by uniform distribution of particles and pores throughout the structure, but with small pores. And in the image of the SPI only gel, it's possible to distinguish the presence of bigger agglomerates with large pores. On the other hand, the mixed protein gel networks present intermediate morphologies between the control gels. But the S30 gel showed the particulate structure of WPI in the SEM image in the large pores of SPI in the confocal image. In the results from uniaxial compression here tests, we can see the same gel showed higher elasticity modulus than the control gel and the other mixed protein gels. Regarding the small deformation tests, the highest storage modulus was also this gel. In the case of this specific gel, this S30, the G-line value during the heating was slightly higher than the G-line of the WPI only gel and lower than the SPI only gel. And the G-line values of the other were lower than both control gels. These results and the morphological results indicate that for the mixed protein gels with 30% of SPI, both proteins contribute to the formation and the strength of the gel network due to the synergy of this ratio mixture. After that, we did the static in vitro digestion simulate the conditions for seniors. For oral phase, we didn't change what was in the INFOGEST 2.0. For gastric phase, we increased the pH and the duration and decreased the pepsin level. And for the intestinal phase, we increased the duration and decreased the pH a little bit and decreased the pancreatin and bile salts level. Protein hydrolysis was determined by quantifying the free amino groups through OPA method. The concentration of free aminos was low for all samples, but the end of the gastric phase showing the proteolysis was similar. The optimum pH for pepsin activity is below 3, and it was used pH 4 for mimic the other digestion in the in vitro experiments. This could explain the limit degree of hydrolysis of the proteins by pepsin, but in the intestinal digestion of all gels lead to increase in the rate of the proteolysis in comparison to the corresponding gastric sample. But S30 and S50 mixed protein gels were digested more easily. This higher digestibility of these gels could be attributed to the structure of the mixed protein matrix composed by the mixture of large agglomerates and particulate structure, and which facilitates the pepsin diffusion, breaking the gel network into more small fragments, which probably made the proteins more accessible in the intestinal phase to the protease from pancreatin. After the gastric phase, the electrolyte profile show all bands corresponding to the samples before digestion. In addition of the pepsin band, independently of the mixture ratio. The molecular weight distribution in the gastric phase changed with the gel composition. SPI only gel showed the strong signal intensities in the higher molecular weights, and as SPI replaced by double PI in the gel's composition, the signal intensities decrease. This behavior occurs because the most abundant proteins in SPI have molecular weight higher than the proteins in double PI, as shown in SDS page results. This here, alpha, line alpha, beta, AS and BS, that's acid subunits and basic subunits, are proteins from SPI, and these two here around 18 kilodaltons are the proteins from double PI. At the end of the intestinal phase, most of the proteins were digested. The electrolyte profile show only one broadband with a molecular weight below 11 kilodaltons, in addition to the all bands characteristics of pancreatine. That's all these bands. Only the double PI, only gel show a weak band of beta Hg, indicated that milk protein was not totally digested. In fact, beta Hg is resistant to pepsin digestion. Results from SEK, size exclusion chromatography, also show a signal corresponding to beta lactobuline around 18 kilodaltons. That appears on the gels with higher rate of double PI, the S30 and the S0. However, by mixing double PI with SPI, the protein digestion is improved since the peak corresponds to beta Hg disappears in the S50 and S70 gels. The patterns found in the chromatograms of digester gels were very similar. However, there seems to be a difference in the signal intensities. We can see the SPI-only gel shows strong signal intensity below 100 daltons, and as double PI concentration increases, the signal intensity decreases, indicating the level of the proteins hydrolyzed. The level of the proteins hydrolyzed into peptides and amino acids by the pancreas was higher. The last result was the bioaccessibility of the vitamins D3 and B12 that was evaluated by quantification of the bioactivities in the superintendent of digestion samples. What we can see here that digestion helped vitamin 3 become more bioaccessible when it reached the intestine, because higher concentration of vitamin D3 in the intestinal phase was found compared to the gastric phase. And since the absorption of vitamin D in the ingest through the diet occurs in the small intestine, especially in the jejunum and ileum, this is a good result. Regarding vitamin B12, there was no difference in its content in the intestinal and gastric phase, which is a very good result too. Despite the absorption of vitamin B12 is restricted to a section of the small intestine, cobalamin must already be bioaccessible in the stomach, because it's there that it binds to our protein and form a complex that transport this vitamin to duodenum, where proteins from pancreatin cells hydrolyze this complex, releasing cobalamin to bind to intrinsic factor, which finally transported to the ileum. The correlation with this microstructure is that mixing seems to improve the bioaccessibility of the vitamin D3, and Vitamin B12 degrades more in the presence of double PI protein in gels at pH 7 because we can see here that the SPI only gel show higher B12 content, and as SPI was replaced by double PI, the content decreased. This happened because vitamin B12 is lost in milk processing due to prolonged heating at neutral pH, and the gels with double PI contains milk proteins in its composition and were heated to 95 degrees for 30 minutes at pH 7. All factors that contribute to the possible degradation of this hydrophilic bioactive. The conclusions of our work was that the combination of the homogenization of the SPI improves its functional properties. Different proteins ratios form gels with different morphologies and rheological properties, and the proteolysis by pepsin was not significant, but most proteins were hydrolyzed by pancreatine into peptides and amino acids in the intestinal phase. And there was a difference in protein digestion when different ratios were used. Mixing SPI with the PI seems to increase protein digestion as well as the bioaccessibility of vitamins. And that's it. I would like to thank you everyone that helped me during my PhD with a lot of people. And thanks for all the contribution. Hi everyone, I'm Marluci Ghiraldi, and today
Thank you very much, Marluci. That was a really interesting.
thank you.
Yes. Sorry. We have. So thank you very much, Marluci. We have a small issue because we are in the same room. So thank you very much for this nice presentation. It's really interesting, and you did a lot of work. So maybe I can start with one question on the vitamin content of the gels before digestion. Did you quantify the vitamin content of each of your gels prepared with the different formulations?
Yeah, it's a good question because we tried to quantify before digestion, but what happened is we tried to break down the gel by a mechanical way and by a chemical way using DTT and urea, but this didn't change the quantification of the vitamin D and decrease the quantification of vitamin B12, and these results was less than the concentration that we added and the concentration that we had before the digestion for these vitamins. So we think that we try quantification using enzymes, which would be better to break the gels, because what happened is the vitamins was trapped into this three-dimensional network, so we couldn't separate them properly. So if we do that as enzymatic way, we think that the results will be like the same that we did after digestion, because we will do digestion anyway with the same enzyme. So we just use the theoretical proportion that we added in the gels, but we know that we lost these vitamins during the heating process with digestion of the gel. So this what happened. So, and we didn't find in the literature other ways to improve this method of extraction before the digestion.
There is a question here. Maybe I don't know if your answer now helped clarify that, but there is a question in the chat.
I'll find it.
So Hanitra is asking, how do you measure the bioaccessibility of vitamin B12 and vitamin D3 from the digester?
Yeah. From the digestion, the vitamin B12, because it's a hydrophilic compound, I just centrifuge the digester samples and filtrate to pass through the HPLC. And the vitamin D, I use acetonitrile that was better than methanol. I tried both. I use a proportion one digester sample and one to the acetonitrile, and did one ultrasound bath, and then vortex and centrifuge, and take just the supernatant and filter it.
Thank you. Before I move on to the next question, there is one question in the chat, but maybe I will ask, but Shannon has one question as well, so maybe I will let her ask this question before we go to the one in the chat.
Okay.
Thanks, Daniela, and thank you, Marluci, for your very nice presentation. I think your work was tackling one of the most, hot topics of now, looking to digestion in the elderly, and that's where I would like to ask a question. So you adapted parameters for the elderly, and did you see any differences in how the aging gastrointestinal tract might be releasing these micronutrients for absorption?
Yeah, this is other part of my work actually. For the static one, I didn't compare the elderly and the adult, but for the semi-dynamic, that's the other chapters of my thesis, yes. Yeah, I could find actually some difference, but I think the biggest difference that I found when I tried to do a meal with all the ingredients, like with protein and lipids and this, when I simulate a real meal compared to simulate just a protein meal. I think the biggest difference that I found was in this part of my work than elderly and adult, especially because when the protein reaches the intestine, the pancreatine just
It's very efficient.
Most of the proteins.
Yeah. Okay. Well, thank you for your answer, Marluci. Over to you, Daniela.
Okay, thank you, Shannon. So maybe just one last question before we finish. Based on the findings from the comparisons between the digestion profiles of the adult and older adult, the question we have in the chat is whether you have considered some applications for developing food for older adults using the gels for nutrient fortification, for example.
It's a good question. Yes, actually. Um, our group here in Brazil, another PhD student is working with this. She's developing cheese with this gel using the same proportion of protein. So it's a food rich in protein, yeah. And yeah, I think she's finishing this process and it's nice. I think she's not using the same vitamins. I think she's using others. I don't remember because I'm not there anymore. I'm in other university now as a postdoc. But yeah, we are doing that.
Okay, thank you very much, Marluci, for presenting your work and for joining us today for this webinar. We wish you all the best for the next your next projects and the next steps in your career. And we are sure your postdoc is going to give really good results as well.
Thank you for the invitation.
So before we end the webinar, I will just share another slide to show you who is going to be presenting next month. Okay. So hopefully you can see my screen. And so we are coming back early in January, on the 8th of January, with Harun Kazi, who did his PhD at Redet Institute in New Zealand. After that, in February, we're going to have a presentation by Cathal Dold, who is doing his finishing his PhD here in Teagasc in Ireland. And he will be followed by Conor, who is also about to finish his Conor Fitzpatrick, who is also about to finish his PhD here in Teagasc on the impact of variations in milk composition and processing on digestion profiles. And he will be presenting on March 5th, 2025. So thank you very much for joining our webinar. And also I want to thank everyone involved in planning and preparing these webinars each month, Cynthia, Ever, and of course Shannon, who is here today. So we wish you a happy holiday season and we'll see you again in the new year.